So in this question, we're told that our plane has an airspeed of 280 kilometers per hour. The pilot wishes the plane to fly on a northern bearing. There is a 50 kilometer per hour wind blowing from the direction south 45 degrees west. We want to calculate the proper heading the pilot should set and calculate the resulting ground speed. This question is a little bit tricky because they give us partial information about two of the vectors that we need to add. So they specify one vector completely, and for the other two vectors involved in this question, they give us either magnitude or direction, but not both. So the first thing to remember is that because this is a plane flying along, the vector statement or the vector addition that we want to do is that our ground speed is going to be equal to our airspeed plus our wind speed. So first thing we want to do is figure out what we know about each of these three vectors: ground speed, airspeed, and wind speed. The one that we know everything about is the wind speed. We know that there's a 50 kilometer per hour wind blowing from the direction south 45 degrees west. So the direction south 45 degrees west is, if I label these here, north, south, east, west, when they say south 45 degrees west, they mean go south and then go 45 degrees to the west. So this angle in here between south and my vector is going to be, and I'll do this in blue so you can see it a little bit better. This angle here between my vector and due south is 45 degrees. So that line is 45 degrees to the west of south. And because my wind is blowing from that direction, this arrowhead has got to point in towards the center. So that's the one vector that we know everything about. We're told the plane has an airspeed of 280 kilometers per hour, but we're not given anything about the direction there. That is what we're being asked to find here. Calculate the proper heading the pilot should set. Because remember, airspeed is what the plane is trying to do, or what the pilot can do with the plane. So we know how fast it can fly. We don't know what heading the pilot is going to set. What else do we know? Well, we know that the pilot wishes the plane to fly on a northern bearing. That's talking about the resultant vector. At the end of the day, we want this plane to fly due north. So there, we're talking about ground speed, or a resultant vector. So we want this to go due north, like that. We don't know how big it's going to be. That's what we have to calculate. The magnitude of that vector is the second thing. So we need to think about what this vector A here is going to look like, so that when we add it to W, it's going to produce something that goes due north. So I think you can sort of see that if the wind is pushing the plane in this direction, we want to sort of have the plane head in that opposite direction, so those two things will sort of balance out and get us something that goes straight north. So we don't know exactly what this direction is, but we kind of know what it is, and we know that it has a magnitude of 280, and our magnitude over here is 50. So that's enough that we can start trying to put together our vector diagram here. So we are going to do A plus W. So we'll just start with W like this. Okay, this is, and the magnitude of W is 50. And we know that A has to do something like this, and the magnitude of A is 280. And that we know that when we add those two together, we get something that goes vertically, okay, because that ground vector, or that ground speed, has got to go due north. Now we've got to work out our angle information. So as always, I'm going to put these little axis things on each of my vertices, so I can start working out where my angle should go. So what angle do we have here? Well, we know the angle between the tip of my wind vector and the vertical. So that 45 degrees is going to go between the tip of this vector and the vertical. So this end here is 45 degrees, right there. How does that help us? How does it help us? Lauren, what did I do wrong? I cannot, because I don't know what this thing up here is. Okay? I don't know that piece in here. So this angle in here. Yep, so I can figure out that that is going to be 45 degrees as well. Okay. That is helpful, but it's not a complete angle in the triangle, right? Because it's from one vector to just to the vertical. Okay. So I'm still looking for sort of one angle that's in those vertices there. Jordan.
So can you make a right angle triangle by cutting the triangle in half?
I can. And how does that help us, Jordan? Oh. Yep. And the third one is just going to be 45 degrees again. So that angle down here is going to be 45 degrees. Or you could have looked at it and seen the little Z pattern there. That's kind of turned on its side. Okay. Once I've got that thing inside my my triangle there, I can start. Yeah, that gives us enough information to start solving the triangle, because I have one angle here, my 45. I know the magnitude or the length of the side opposite it, and I know the length of one of my other sides. So I can use sine law to figure out the size of this angle up here. So I'm going to call that theta. So I know that sine theta over, let's see, the opposite side is 50, is going to be sine 45, that angle that I've got inside the triangle, divided by the magnitude of the opposite side, which is going to be 280. So I can punch that into my calculator, take the inverse sine, and I get that theta is 7.25 degrees. Now, how does that help us? Well, if this angle right here is theta, that means this angle over here is theta as well, right? Because of that Z pattern. And that angle at the tail of our vector A is a step in getting this proper heading that the pilot should set. So we want the pilot to go what appears to be 7.25 degrees to the west of north. Okay? So the heading should be, it should be north 7.525 degrees west. Okay? So that's the heading that our pilot should set. Okay? The next thing we want to figure out is what our ground speed is going to be. So we need to figure out what the magnitude of this third side is. Well, now that we know this angle out here, we can work out what that angle is inside the triangle. So this little part from here to here is going to be, well, what is it going to be? It's going to be 90 minus 7.25, okay, because the red part there and theta have to add up to 90 degrees. So that gets us, what, 82.75 degrees. And then that whole angle that is opposite side G has got to be 45 degrees plus that 82.75. So that's this whole angle here like that is going to be, if we add those up, we get 127.75 degrees. Now, if we look at side G here, we know the angle opposite, we know the two lengths of the two sides on opposite side, So we've got two sides, the enclosed angle. We can use cosine law to figure out the magnitude of g there. So magnitude of g squared is going to be, what are our sides? They are 280 squared plus 50 squared minus 2 times 280 times 50 times the cosine of the angle between them, 127.75. So we put that into our calculator, work it all out, take the square root, and we get that the magnitude of g, sorry, we'll actually take the square root when we give our final answer. The magnitude of g is 313.12 kilometers per hour. So in our original question, we were asked to find two things: the proper heading, which we got in our first step here, and the resulting ground speed. We've got the magnitude right here, okay? And we know that the direction is going to be north because we were given that in the question. So magnitude is this. So G is in northerly direction. Let's just say due north. And there we are, the two things that we were asked for in the question.